Geomorphology is the scientific study of landforms and the processes that shape them. Geomorphologists seek to understand why landscapes look the way they do, to understand landform history and dynamics, and to predict changes through a combination of field observations, physical experiments and numerical modeling. Geomorphology is practiced within physical geography, geology, geodesy, engineering geology, archaeology and geotechnical engineering. This broad base of interest contributes to many research styles and interests within the field. Overview. Geomorphology studies in particular the lithosphere, and interactions with the atmosphere and hydrosphere, to understand the interconnection of various system processes. Geomorphologists are particularly interested in the potential for feedbacks between climate and tectonics mediated by geomorphic processes. Geochronology uses dating methods to measure the rate of changes. Terrain measurement techniques include differential GPS, remotely sensed digital terrain models and laser scanning, to quantify, study, and to generate illustrations and maps. The surface of Earth is modified by a combination of surface processes that sculpt landscapes, and geologic processes that cause tectonic uplift and subsidence, and shape the coastal geography. Surface processes comprise the action of water, wind, ice, fire, and living things on the surface of the Earth, along with chemical reactions that form soils and alter material properties, the stability and rate of change of topography under the force of gravity, and other factors, such as human alteration of the landscape. Many of these factors are strongly mediated by climate. Geologic processes include the uplift of mountain ranges, the growth of volcanoes, isostatic changes in land surface elevation, and the formation of deep sedimentary basins where the surface of Earth drops and is filled with material eroded from other parts of the landscape. The Earth's surface and its topography therefore are an intersection of climatic, hydrologic, and biologic action with geologic processes. The broad-scale topographies of Earth illustrate this intersection of surface and subsurface action. Mountain belts are uplifted due to geologic processes. Denudation of these high uplifted regions produces sediment that is transported and deposited elsewhere within the landscape or off the coast. On progressively smaller scales, similar ideas apply, where individual landforms evolve in response to the balance of additive processes and subtractive processes. Often, these processes directly affect each other. Ice sheets, water, and sediment are all loads that change topography through flexural isostasy. Topography can modify the local climate, for example through orographic precipitation, which in turn modifies the topography by changing the hydrologic regime in which it evolves. In addition to these broad-scale questions, geomorphologists address issues that are more specific and/or more local. Glacial geomorphologists investigate glacial deposits such as moraines, eskers, and proglacial lakes, as well as glacial erosional features, to build chronologies of both small glaciers and large ice sheets and understand their motions and effects upon the landscape. Fluvial geomorphologists focus on rivers, how they transport sediment, migrate across the landscape, cut into bedrock, respond to environmental and tectonic changes, and interact with humans. Soils geomorphologists investigate soil profiles and chemistry to learn about the history of a particular landscape and understand how climate, biota, and rock interact. Other geomorphologists study how hillslopes form and change. Still others investigate the relationships between ecology and geomorphology. Because geomorphology is defined to comprise everything related to the surface of Earth and its modification, it is a broad field with many facets. Practical applications of geomorphology include hazard assessment, river control and stream restoration, and coastal protection. Planetary geomorphology studies landforms on other terrestrial planets such as Mars. Indications of effects of wind, fluvial, glacial, mass wasting, meteor impact, tectonics and volcanic processes are studied. This effort not only helps better understand the geologic and atmospheric history of those planets but also extends geomorphological study of Earth. Planetary geomorphologists often use Earth analogues to aid in their study of surfaces of other planets. History. With some notable exceptions, Geomorphology is a relatively young science, growing along with interest in other aspects of the earth sciences in the mid-19th century. This section provides a very brief outline of some of the major figures and events in its development. Ancient geomorphology. The first theory of geomorphology was arguably devised by the polymath Chinese scientist and statesman Shen Kuo. This was based on his observation of marine fossil shells in a geological stratum of a mountain hundreds of miles from the Pacific Ocean. Noticing bivalve shells running in a horizontal span along the cut section of a cliffside, he theorized that the cliff was once the prehistoric location of a seashore that had shifted hundreds of miles over the centuries. He inferred that the land was reshaped and formed by soil erosion of the mountains and by deposition of silt, after observing strange natural erosions of the Taihang Mountains and the Yandang Mountain near Wenzhou. Furthermore, he promoted the theory of gradual climate change over centuries of time once ancient petrified bamboos were found to be preserved underground in the dry, northern climate zone of Yanzhou, which is now modern-day Yan'an, Shaanxi province. Early modern geomorphology. The term geomorphology seems to have been first used by Lohmann in an 1858 work written in German. Keith Tinkler has suggested that the word came into general use in English, German and French after John Wesley Powell and W. J. McGee used it during the International Geological Conference of 1891. An early popular geomorphic model was the geographical cycle or cycle of erosion model of broad-scale landscape evolution developed by William Morris Davis between 1884 and 1899. It was an elaboration of the uniformitarianism theory that had first been proposed by James Hutton. With regard to valley forms, for example, uniformitarianism posited a sequence in which a river runs through a flat terrain, gradually carving an increasingly deep valley, until the side valleys eventually erode, flattening the terrain again, though at a lower elevation. It was thought that tectonic uplift could then start the cycle over. In the decades following Davis's development of this idea, many of those studying geomorphology sought to fit their findings into this framework, known today as Davisien. Davis's ideas are of historical importance, but have been largely superseded today, mainly due to their lack of predictive power and qualitative nature. In the 1920s, Walter Penck developed an alternative model to Davis's. Penck thought that landform evolution was better described as an alternation between ongoing processes of uplift and denudation, as opposed to Davis's model of a single uplift followed by decay. Penck's ideas were not recognized until many years after his death, perhaps because his work was not translated into English. He was involved in disputes with Davis, and he died young. Both Davis and Penck were trying to place the study of the evolution of the Earth's surface on a more generalized, globally relevant footing than it had been previously. In the early 19th century, authors, especially in Europe, had tended to attribute the form of landscapes to local climate, and in particular to the specific effects of glaciation and periglacial processes. In contrast, both Davis and Penck were seeking to emphasize the importance of evolution of landscapes through time and the generality of the Earth's surface processes across different landscapes under different conditions. During the early 1900s, the study of regional-scale geomorphology was termed physiography. Physiography later was considered to be a contraction of physical and geography, and therefore synonymous with physical geography, and the concept became embroiled in controversy surrounding the appropriate concerns of the discipline. Some geomorphologists held to a geological basis for physiography and emphasized a concept of physiographic regions, while a conflicting trend among geographers was to equate physiography with pure morphology, separated from its geological heritage. In the period following World War II, the emergence of process, climatic, and quantitative studies led to a preference by many earth scientists for the term geomorphology in order to suggest an analytical approach to landscapes rather than a descriptive one. Quantitative geomorphology was started to be put on a solid quantitative footing in the middle of the 20th century. Following the early work of Grove Carl Gilbert around the turn of the 20th century, a group of natural scientists, geologists and hydraulic engineers including Ralph Alger Bagnold, Hans Albert Einstein, Frank A. Nert, John Hack, Luna Leopold, A. Shields, Thomas Maddock and Arthur Strahler began to research the form of landscape elements such as rivers and hill slopes by taking systematic, direct, quantitative measurements of aspects of them and investigating the scaling of these measurements. These methods began to allow prediction of the past and future behavior of landscapes from present observations, and would later to develop into what the modern trend of a highly quantitative approach to geomorphic problems. Quantitative geomorphology can involve fluid dynamics and solid mechanics, geomorphometry, laboratory studies, field measurements, theoretical work, and full landscape evolution modeling. These approaches are used to understand weathering and the formation of soils, sediment transport, landscape change, and the interactions between climate, tectonics, erosion, and deposition. Contemporary geomorphology. Today, the field of geomorphology encompasses a very wide range of different approaches and interests. Modern researchers aim to draw out quantitative laws that govern Earth surface processes, but equally, recognize the uniqueness of each landscape and environment in which these processes operate. Particularly important realizations in contemporary geomorphology include, 1. That not all landscapes can be considered as either stable, or perturbed, where this perturbed state is a temporary displacement away from some ideal target form. Instead, dynamic changes of the landscape are now seen as an essential part of their nature. 2. That many geomorphic systems are best understood in terms of the stochasticity of the processes occurring in them, that is, the probability distributions of event magnitudes and return times. This in turn has indicated the importance of chaotic determinism to landscapes, and that landscape properties are best considered statistically. The same processes in the same landscapes do not always lead to the same end results. Processes. Geomorphically relevant processes generally fall into the production of regolith by weathering and erosion, the transport of that material, and its eventual deposition. Primary surface processes responsible for most topographic features include wind, waves, chemical dissolution, mass wasting, groundwater movement, surface water flow, glacial action, tectonism, and volcanism. Other more exotic geomorphic processes might include periglacial processes, salt-mediated action, or extraterrestrial impact. Aeolian processes. Aeolian processes pertain to the activity of the winds and more specifically, to the wind's ability to shape the surface of the Earth. Winds may erode, transport, and deposit materials, and are effective agents in regions with sparse vegetation and a large supply of fine, unconsolidated sediments. Although water and mass flow tend to mobilize more material than wind in most environments, aeolian processes are important in arid environments such as deserts. Biological processes. The interaction of living organisms with landforms, or biogeomorphologic processes, can be of many different forms, and is probably of profound importance for the terrestrial geomorphic system as a whole. Biology can influence very many geomorphic processes, ranging from biogeochemical processes controlling chemical weathering, to the influence of mechanical processes like burrowing and tree throw on soil development, to even controlling global erosion rates through modulation of climate through carbon dioxide balance. Terrestrial landscapes in which the role of biology in mediating surface processes can be definitively excluded are extremely rare, but may hold important information for understanding the geomorphology of other planets, such as Mars. Fluvial processes. Rivers and streams are not only conduits of water, but also of sediment. The water, as it flows over the channel bed, is able to mobilize sediment and transport it downstream either as bed load, suspended load or dissolved load. The rate of sediment transport depends on the availability of sediment itself and on the river's discharge. Rivers are also capable of eroding into rock and creating new sediment, both from their own beds and also by coupling to the surrounding hill slopes. In this way, rivers are thought of as setting the base level for large-scale landscape evolution in non-glacial environments. Rivers are key links in the connectivity of different landscape elements. As rivers flow across the landscape, they generally increase in size, merging with other rivers. The network of rivers thus formed is a drainage system and is often dendritic, but may adopt other patterns depending on the regional topography and underlying geology. Glacial processes. Glaciers, while geographically restricted, are effective agents of landscape change. The gradual movement of ice down a valley causes abrasion and plucking of the underlying rock. Abrasion produces fine sediment, termed glacial flour. The debris transported by the glacier, when the glacier recedes, is termed a moraine. Glacial erosion is responsible for U-shaped valleys, as opposed to the V-shaped valleys of fluvial origin. The way glacial processes interact with other landscape elements, particularly hillslope and fluvial processes, is an important aspect of Pleistocene landscape evolution and its sedimentary record in many high mountain environments. Environments that have been relatively recently glaciated but are no longer may still show elevated landscape change rates compared to those that have never been glaciated. Non-glacial geomorphic processes which nevertheless have been conditioned by past glaciation are termed paraglacial processes. This concept contrasts with paraglacial processes, which are directly driven by formation or melting of ice or frost. Hillslope processes. Soil, regolith, and rock move downslope under the force of gravity via creep, slides, flows, topples, and falls. Such mass wasting occurs on both terrestrial and submarine slopes, and has been observed on Earth, Mars, Venus, Titan and Iapetus. Ongoing hillslope processes can change the topology of the hillslope surface, which in turn can change the rates of those processes. Hillslopes that steepen up to certain critical thresholds are capable of shedding extremely large volumes of material very quickly, making hillslope processes an extremely important element of landscapes in tectonically active areas. On Earth, biological processes such as burrowing or tree throw may play important roles in setting the rates of some hillslope processes. Igneous processes. Both volcanic and plutonic igneous processes can have important impacts on geomorphology. The action of volcanoes tends to rejuvenize landscapes, covering the old land surface with lava and tephra, releasing pyroclastic material and forcing rivers through new paths. The cones built by eruptions also build substantial new topography, which can be acted upon by other surface processes. Plutonic rocks intruding then solidifying at depth can cause both uplift or subsidence of the surface, depending on whether the new material is denser or less dense than the rock it displaces. Tectonic processes. Tectonic effects on geomorphology can range from scales of millions of years to minutes or less. The effects of tectonics on landscape are heavily dependent on the nature of the underlying bedrock fabric that more or less controls what kind of local morphology tectonics can shape. Earthquakes can, in terms of minutes, submerge large areas of land creating new wetlands. Isostatic rebound can account for significant changes over hundreds to thousands of years, and allows erosion of a mountain belt to promote further erosion as mass is removed from the chain and the belt uplifts. Long-term plate tectonic dynamics give rise to orogenic belts, large mountain chains with typical lifetimes of many tens of millions of years, which form focal points for high rates of fluvial and hillslope processes and thus long-term sediment production. Features of deeper mantle dynamics such as plumes and delamination of the lower lithosphere have also been hypothesized to play important roles in the long-term, large-scale evolution of the Earth's topography. Both can promote surface uplift through isostasy as hotter, less dense, mantle rocks displace cooler, denser, mantle rocks at depth in the Earth. Scales in geomorphology. Different geomorphological processes dominate at different spatial and temporal scales. Moreover, scales on which processes occur may determine the reactivity or otherwise of landscapes to changes in driving forces such as climate or tectonics. These ideas are key to the study of geomorphology today. To help categorize landscape scales, some geomorphologists might use the following taxonomy: first, continent, ocean basin, climatic zone; second, shield, for example Baltic Shield, or mountain range; third, isolated sea, Sahel; fourth, massif, for example Massif Central or group of related landforms, for example, Weald; fifth, river valley, Cotswolds; sixth, individual mountain or volcano, small valleys; seventh, hill slopes, stream channels, estuary, 8th, gully, bar canal, 9th, meter-sized features, overlap with other fields. There is a considerable overlap between geomorphology and other fields. Deposition of material is extremely important in sedimentology. Weathering is the chemical and physical disruption of earth materials in place on exposure to atmospheric or near-surface agents, and is typically studied by soil scientists and environmental chemists, but is an essential component of geomorphology because it is what provides the material that can be moved in the first place. Civil and environmental engineers are concerned with erosion and sediment transport, especially related to canals, slope stability, water quality, coastal environmental management, transport of contaminants, and stream restoration. Glaciers can cause extensive erosion and deposition in a short period of time, making them extremely important entities in the high latitudes and meaning that they set the conditions in the headwaters of mountain-borne streams. Glaciology therefore is important in geomorphology. See also. References. Further reading, Chorley, Richard J. Stanley Alfred Schumann, David E. Sugden. Geomorphology. London, Methuen. ISBN A0-416-32590-4, Committee on Challenges and Opportunities in Earth Surface Processes, National Research Council. Landscapes on the Edge, New Horizons for Research on Earth's Surface. Washington, D.C., National Academies Press. ISBN A0-309-14024-2. Meyer, Bernhard. Earthsol. London, Phaidon Press. ISBN A0-7148-4451-9. Condolf, G. Matthias. Herva Copyright Peer Copyright Gay. Tools in Fluvial Geomorphology. New York, Wiley. ISBN A0-471-49142 Exa, Cuenza, Claudia. Strachur, Glenn B. Geomorphology of Coal Seam Fires. Geomorphology 138, 209 €222. Bibcode, 2012 Geomo 138-209 KDOI, 10.1016/J Geomorph. 2011.09.004. Needham, Joseph. Science and Civilization in China. Cambridge, UK, Cambridge University Press. ISBN A0-521-05801-5. Yadega, Adrian E. Morphotectonics. Berlin, Springer. ISBN A3-540-20017-7. Selby, Michael John. Earth's Changing Surface, An Introduction to Geomorphology. Oxford, Clarendon Press. ISBN A0-19-823252-7. Charlton, Rue. Fundamentals of Fluvial Geomorphology. London, UK, Routledge. ISBN A978-0-415-33454-9. External links, The Geographical Cycle, or the Cycle of Erosion, Geomorphology from Space.